Here we go. Okay, we are recording. So here we are. Today, we're going to dive into section 9.5. Okay, section 9.5, it's all about a particular type of relation that's really common and useful in a certain way. So that type of relation is called an equivalence relation. There's a lot of different examples of equivalence relations, but some of them are very, very familiar. The most familiar example of an equivalence relation is equals. It's the most basic type of equivalence relation. Equals. Two elements are equal if they're actually the same element. Instead of two distinct things, it's actually just the same thing. So everything is equal to itself, but nothing else. So that is the most basic example of an equivalence relation, but there are tons of other ways to make equivalence relations. And the rules, so the thing that really defines an equivalence relation is that it has these three properties. It's reflexive, every element is related to itself, equivalent to itself. It's symmetric, if x is equivalent to y, then y is equivalent to x, symmetric. And also transitive, if x is equivalent to y and y is in turn equivalent to z, x will also be equivalent to z. Okay, so that's transitive. So any relation that has these three properties can be called an equivalence relation. And we have special notation for equivalence relations. Instead of writing x r y, you can write x tilde y. Tilde. Is that what you write that? I call that tilde. X squiggle. I'll pretty much just pronounce this as x is equivalent to y. So that is our generic symbol for an equivalence relation. But there's a bunch of other symbols that you'll see used for equivalence relations. I mean, like I've already said, equals is one of them, but equals is a very specific relation. You'll also see this notation here used to mean equivalence. So either of those notations, either of those symbols is a generic equivalence symbol, okay? So let's look at an example. So here's an example which is defined by a digraph. So yesterday we introduced this idea of a digraph, where the arrows represent the relations and the nodes represent the elements in the set. So here we have a finite set A, B, C, D, E, F, and those six elements are just represented as dots on this diagram. The location of them or the way they're arranged is completely irrelevant to the structure of the relation. The relation is entirely determined by the arrows between them. So every single one of these nodes has a looping arrow on it. That's because it has to be reflexive, right? So reflexive is reflected by the loops. The symmetric property is that every time there's an arrow between distinct nodes, there's another arrow going back the other direction. So you'll see every time there's an arrow between different elements that we have both arrow directions going on. That's symmetry, the symmetric property. And then the transitive property is exhibited over here in the triangle between A, B, and D. If you go from, say, for example, B to A and then A to D, you have to also be able to go from B to D. So it's sort of like the fact that this triangle is a complete triangle, that makes it satisfy the transitive property. So yeah, so that is an equivalence relation. And now I'm going to use this example to introduce this idea of an equivalence class. An equivalence class is basically it's an equivalence class of a particular element, and you can pick any element you want. The equivalence class of that element is, with respect to the relation you're talking about, right, is basically, it's the set of all elements that are related to that element. So it's defined like this, and the notation is with these square brackets here. It's defined like that. The equivalence class of A with respect to the relation R is equal to the set of all elements X in the domain, such that X is related to A. That's it. X is equivalent to A. So one thing you'll be certain of is that every element is a member of its own equivalence class because of the fact that it's reflexive. So like A is an element of the equivalence class of A, and as is every other thing which is related to A by the equivalence relation. So in the example 1 up here, if you look at the element A, the element that's actually called A, this one, its equivalence class is going to contain itself as well as everything that it's related to, which would be the B and also D. So the equivalence class of A is A, B, D. You can see that I wrote that right here, A, B, and D. That exact same set containing A, B, and D is also the equivalence class for B. Oops, sorry. It's also the equivalence class for B, and it's also the equivalence class for D. So all the members of that equivalence class, if you say, hey, you element, what's your equivalence class? They'll report back to you the same information. So if you take any element in that class and say, what's your equivalence class? They'll report to you and say, I am in this equivalence class. And they'll tell you the same thing because they're all together, right? But if you take another element like E, right? But the equivalence class of the element E, that's different because E is like in another sort of disconnected group over here, right? E is connected with F over here. And so E will tell you its equivalence class is itself and F. Does that make sense? If you asked F, what's your equivalence class? F would tell you the same thing. It's E and F. Okay. So equivalence classes, when you represent an equivalence class with that bracket notation with like a representative inside it, that element you're asking for the equivalence class of, it's basically like serving as just a representative from the class. Okay. It could be any of them, and it would represent the same set. Does that kind of make sense? Let's see if I have the chat open here. Where's the chat? There's the chat. Yeah. Okay, so here's a question. What's the equivalence class of the element C in this example up above? Just C. It's a set. Caleb's got it. Perfect. It's a set containing C. That's it. So we could write here. The equivalence class of C with respect to this relation R is just the set containing C because it's only related to itself and nothing else. Okay. So before we move on to the next example, I want to do a little exercise here. Let's do a little exercise together. Let's construct our own equivalence relation. I have 6 elements, A, B, C, D, E, F again. Somebody give me somebody give me an ordered pair of elements. We're gonna throw in a couple of relationships here, just sort of randomly. I want about 3 or 4, between 3 and 5 different relationships between things. Give me some ordered pairs, people. Ordered pairs of the elements A, B, C, D, E, F. Calling on you for some participation. Thanks, Caleb. Thanks, Dominic. Okay, so we go BE. All right, BE, we get that one. We've got DB, D and B, those ones. And then Rabes gives me A and C. Oh, hang on. Dominic said DB. Let's go backwards that way. And then A and C, like that. Anything else? Let's have one more. Okay, I'm gonna take Lily's here, FD. Right, that's it. So let's just take those. So what I want to do is I want to go ahead and complete, these are all relationships in a relation. What if we want to take this and sort of complete this to form an equivalence relation? What we're going to need to do is we're going to need to make sure that we satisfy all of the types of relationships that you could have between things. We're going to make sure that we satisfy the three conditions: reflexive, symmetric, and transitive. So we're going to have to add in some more relationships beyond what we already have written here. So let's start with transitive. So since, for example, F is related to D and D in turn is related to B, we're going to need to add in a relationship that goes from F to B. So that one will be required in order to satisfy the transitive property. Does that make sense? F goes to D, D goes to B, so we've got to go F directly to B. Now, we also have D is related to B and B is related to E. D to B, B to E. So I've got to go D to E like that. Can anyone see any other triangles that need to be completed in order to satisfy the transitive property? So we currently don't have, oh yeah, Dominic said BDE and then corrected it to FDE. FDE, great, yes, F goes to D and D goes to E. So, so F goes to D, D goes to E. So we do have to go from F to E. Melody said E to F. So E doesn't actually go anywhere. We don't have any arrows coming away from E. So we don't have to, so there's nothing that's going to come starting from E. We did need to go F to E. So we did need to go the other direction because of the F to D, D to E. And also actually, yeah, going to make sure we kind of keep the direction, make sure we're thinking about the direction. We also had another reason for going from F to E because we also had F to B and B to E. So there's another reason why we needed to complete. So that sort of completed two separate triangles for us. So that's good. I think with those three extra arrows, I think we've now satisfied the transitive property completely on this graph. So the next thing I want to do is try to satisfy the symmetric property. So for the symmetric property, this is going to be kind of easy. All we have to do is go around, and for every arrow, we're going to put another arrow going back the opposite direction. So like that arrow from A to C requires an arrow going back from C to A. And B to the F to B, we're going to have to go backwards, B to F, and we're going to have to go backwards here. And we're going to have to go backwards like this. And we're going to have to go like this direction. We're going to have to go like this and like this. So I think I did all the backwards arrows. So that now I've made it satisfy the symmetric property. And then finally, to make it satisfy reflexive, what we need to do is go around and put loops on every single element. So all the elements require loops. Okay, there we go. So there we go. So now this is the equivalence class closure, you could say. Like we've kind of completed the relation so that it now satisfies all of the conditions of an equivalence relation. And so now this is what we call the smallest equivalence relation that contains the relationships we initially started with, the ones that you gave me. Okay, it's the minimum possible. It's like this, yeah, it's the simplest equivalence relation that has all those conditions that we started with. So now we can look at this and ask, what are the equivalence classes? Somebody write down an equivalence class. For this relation. See if you can figure out what those are going to be. How many are there? How many distinct equivalence classes are there? what you want to do is you want to go around looking for the like subsets of our domain that are connected to each other, basically like the connected components of the graph. So for example, A and, oops, meant to make that like yellow. A and C here together form a connected component where A and C are connected to each other, but that's actually, A and C are like disconnected from the rest of the graph. There's no connections between A and C and the other elements, right? So A and C together form their own from their own equivalence class, AC, like that. And this you could call this the equivalence class of A. You could also call it the equivalence class of C. Either one. Okay. So that's one equivalence class. And the other equivalence class, we'll highlight it with like a nice bright blue here. The other equivalence class is going to be B and F and D and E all together because of all those connections. And this one. I'm sort of highlighting the elements and also the connections between them there. Okay. So those four together form their own equivalence class B, F, D, E. And it doesn't matter what order you write them in because it's a set. Like that. And so, for example, this could be the equivalence class of F, but, you know, also the equivalence class of D, or the equivalence class of E or B. Okay, so there we go. So that is this little exercise I wanted to go through. Any questions about that? It's an exercise in constructing our own equivalence relation and studying it and identifying its equivalence classes. Okay, let's look at a few more examples of equivalence relations. So example 2, congruence modulo M, something we learned about back in chapter 4. I want to say it was chapter 4 when we did number theory. We talked about like congruence, reducing things, mod M. That congruence modulo M is actually an equivalence relation you can define on integers. For example, if we pick the modulus 10, then here's my example. The equivalence class of the number 7 is this, right? So we have, these are all the numbers. These aren't all of them. I put ... at the beginning and the end because there's an infinite number of different integers that are congruent to 7 mod 10, right? There's the distance between these numbers is 10. If you keep adding 10 or subtracting 10, you can get infinitely many numbers in this set. So you can write it like this. It's a set of all integers n such that n minus 7 is a multiple of 10. Okay. So there's another example of equivalence classes. And the equivalence classes are the sort of like all the things that are congruent to 1 and all the things that are congruent to 2 and all the things that are congruent to 3 and so on and so on. And there's 10 of them because when you do mod 10, there's 10 distinct equivalence classes you get out of that. And so on. If you were to do mod 12, you'd have 12 distinct equivalence classes that you'd get. And every single integer would fall into one of those equivalence classes. Right. Here's another example. On the set people, the relation was born in the same year as is also an equivalence relation. It's reflexive. You're born in the same year as yourself. It's symmetric. If you and I are born in the same year, then I and you are also born in the same year. It goes both ways. And then it's transitive. You can kind of work that one through in your head. It's transitive as well. So my example of my equivalence class, the equivalence class of Tristan, is the set of all people born in 1989. Okay. Last year of the 80s, I barely made it. I just barely squeezed in right before the 80s ended. Oh. All right. So that's equivalence classes. Pretty straightforward idea, really common thing that you like use in lots of different fields of mathematics. Okay. So now we're going to turn our attention to a separate idea called partition of a set. This is really nothing to do with relations initially. We're going to tie it in, but this is just something you can define. A partition is just something you can define using set theory. It's just an idea of like taking a collection of subsets of something. So a partition of a set A is a collection of subsets. We're just going to call them AI, where I is some sort of index set. If it's a finite number of sets, then I is probably going to be like the set of numbers, integers 1, 2, 3, 4, 5, 6, up to however many of them there are. It's possible to have an infinite partition. An infinite partition just has an infinite number of sets in the collection. That's fine. And then your index set might be like the set of all natural numbers or something, if it's countable. Technically, you can have an uncountably infinite partition. So your index set that you're using might be like the real numbers or something. Something uncountable. So like you can have lots of different things that you're using as an index set there. But basically, that's what I is. It's just the index, the set of all indices that you use to label the sets in the partition. So the partitions are these AIs. These AIs are subsets of A. And in order to be called a partition, it needs to satisfy these two conditions. One is that the union of all the AIs is A itself. So that just basically means that the AIs sort of cover all of the elements in A. Everything's covered. Every element in A is going to be an element of at least one of the sets, the subsets that form the partition. Okay, and the other special rule it has to satisfy is that distinct subsets in the collection have to be what's called disjoint, which means that their intersection is empty. So there's no overlap between the subsets. So that's the two things you need to call the collection of subsets a partition of the total set. They cover the whole thing, and there's no overlap between the subsets. So here's a sort of a diagram that just kind of basically explains that idea. Here is the entire set A represented by this blob. And if we cut that blob up into pieces and label every one of the pieces as a separate subset, that forms a partition. So the partition of A is the collection of subsets A1 through A7. Okay. So that's a super straightforward kind of like, just kind of a mental image of what a partition is. Okay. Any questions about partitions? Use partitions in a lot of situations. Every time we form breakout rooms, every time we go into breakout rooms, that is forming a partition of the set of students in this class, right? And it's sort of a randomly selected partition. When I assigned your groups for the project, I was creating a partition of the set of students in this class. That makes sense? Because every student is in a group. Almost, it will be. I think I've got like one more student to assign. I'm kind of waiting to hear back on an email from somebody. But every student will be in a group, and no student will be in more than one group. So there's no overlap. All right, so we've got partitions. So now the kind of culminating part of this section, the culminating theorem of this section 9.5 is to say, it's this theorem, it's the partition theorem. It's to say, hey, basically the idea of an equivalence relation on a set and the idea of a partition of a set are actually the exact same thing. They're completely equivalent ideas. And you can translate back and forth between the idea of an equivalence relation defined on a set and the idea of a partition of a set. And the key that connects those two ideas is the equivalence classes. So the theorem goes like this. If R is an equivalence relation defined on a set A, then the separate distinct equivalence classes for that relation R form a partition of A. Every element is in an equivalence class, and the equivalence classes have no overlap, so that's a partition. So going back to like our examples, in this example here, you can see the different possible, darn it, I don't know why that didn't work. So here you can see the different equivalence classes. There's one equivalence class. Here's another equivalence class. And there's another equivalence class. So those are the equivalence classes, and they form a partition of the set A, right? Going back to this example, the equivalence classes are here, the yellow one, this one, and the blue one, this one. Those two sets, subsets of A, they also form a partition of A, different partition, right? So in these two examples that we were looking at with the digraphs, it's the same overall set, but the actual equivalence relations we defined on them are different, and they produced different partitions through their equivalence classes. Okay. So with congruence modulo 10, in that other example, the equivalence classes, like the congruence classes, what they're called, they are an infinite partition of the set of integers. Okay. 10, or sorry, they're not an infinite partition. It's a finite partition. There's only 10 sets, but the sets themselves are infinite. That's what I meant. So that's the idea of, so that's going one direction. And then the going the other direction of the proof just says, hey, if you have a partition of a set A, then there is an equivalence relation on that set whose distinct equivalence classes are the subsets in the partition. So that's it. So just going back and forth, we have this like connected, this way to connect and translate back and forth both directions between these two notions. Okay, there's a long proof in the textbook. It sounds like a pretty straightforward idea. It actually is very intuitive, I think, but the proof sort of takes a long time. So I'm not going to go through it. But it's pretty cool because you'll discover one of the things I like about the proof that kind of make me regret not taking the time to do it in class is that it does demonstrate in the proof, it demonstrates why the three conditions for an equivalence relation, reflexive, symmetric, and transitive, are all important, because all three of those conditions you end up having to rely on each of them in the proof. So the proof takes those three conditions and uses them. All three of them are essential to proving this relationship with partitions. So that's kind of cool. The proof kind of highlights the importance of all three of those properties in this theorem. But anyway, I'll leave it to you to read that theorem and its proof in the book. So that concludes the lesson on 9.5. Does anybody have questions? There's a question, will you need to draw a digraph on a test, or will you be analyzing existing digraphs? I might ask you to draw a digraph. Either one. I might ask you to draw a digraph, or I might show you a digraph and ask you to do something with it. Is that all right? Are we okay to draw digraphs? I always draw them with a stylus on a computer and then just copy paste the image into a document. So like that's how I did this one, for example. I just drew this on with my stylus on the drawing app and then copy pasted it in. But that's because I have a touch screen. If you don't have a touch screen, you can also do it in Microsoft Word. I'll show you real quick how you can draw digraphs in Microsoft Word. You can do stuff like A, B, C, D, E, or something. And then you can, in the draw, well, you can draw. So if you have a touchscreen, you can draw. But if you're just using a mouse, you can go into shapes and grab arrows and then do stuff like that. And that. And so on. So that's one way to do it. And to make loops, how do you make loops? I can't remember how I used to make loops. I've done this before. Freeform scribble. Yeah, you might have to just draw the loops like that. Or you could just write a comment, like just pretend all of these have loops on them. And then I'll be like, okay, that's fine. If the drawing is really hard. It's another question. When is the test coming up? So so the test on this topic is not for quite a while. We do have a little D2L sort of review. I haven't written it yet. I've got to write that ASAP because that's supposed to be due Sunday. So I'll get that out to you as soon as I can. But that's coming up soon. That's coming up like this weekend. It's going to be a short little like review quiz on D2L, multiple choice, similar to the one you did for Unit 2. Okay. So you got that coming up. The actual test for that's going to cover chapter 9 is not gonna, we're not going to get there until after we've gotten through chapter 10 as well. And that is on April 7th. Another question about homework. I am going to do the self-assessment on the homework for the rest of the semester, assuming that it goes well. But I'm planning on switching over to that method from here on out. I do want you to submit it. I do want you to like scan it and submit it so that I can cross-reference if necessary. But I will be taking your, for the most part, I'm going to be taking your word for on the score. Okay, that'll just kind of simplify things for me a lot. Okay, we are still recording. Any other questions? Yeah, good question. Is there homework for chapter 9? You know, I'll get back to you on that. I haven't posted it yet. I do actually have homework for chapter 9, but I was debating whether I was going to even give you any. We might just skip homework for chapter 9. I'll put some. I'll put it on like the first worksheet. But I'll get back to you on that. Like I said, I'll get back to you. Oh, I'm so behind. So behind. All right. Before I embarrass myself too much with other ways in which I am behind, let's go ahead and wrap up the lesson for today. We have about 10 minutes, which is perfect. So I just wanted to introduce to you all one other special type of relation, because we've put out there, hey, there are these things, special things called equivalence relations. There's another special type of relation, of course, called a function that we already learned about a while ago, right? Functions are a special type of relation that satisfy a special rule. But then there's another special type of relation I want to tell you about, which is a thing called a partial order. This is a little bit of section 9.6 here. Partial order. A partial order, instead of reflexive, symmetric, and transitive, a partial order is reflexive, anti-symmetric, and transitive. Okay, so an example of this is the less than or equal to relation, defined on either integers or real numbers, natural numbers, numbers of any kind. So defined on like natural numbers, integers, real numbers, any numbers, whatever. Not not complex numbers. Complex numbers are harder. Because complex numbers aren't like aren't linear, right? Complex numbers can't be lined up on a line. So less than or equal to, or less than in general, is like not really well defined for complex numbers. Tricky. It's much harder to define an ordering on complex numbers, but you can define one on real numbers. So so less than or equal to. Less than or equal to is reflexive because of the or equal to part. It's anti-symmetric, as we've talked about before, and it is transitive, as we've talked about before. So that's a partial order. The reason it's called partial order is because in general, you don't need to necessarily have any two elements comparable to one another. However, with this as our typical example, any two elements are comparable. Let's define what we mean by comparable. Give me a second here. So given two elements x and y in a set A, oops, sorry, it's one of those days. Given x and y in a set A, if either x is like related to y or y is related to x, then x and y are called comparable. Okay, they're called comparable. So there's some examples where things aren't comparable. But that's why it's called a partial order, because basically the idea is that the relation establishes what order the elements go in. Like less than or equal to can establish, like can be used to establish that this, 2 comes before 5. So it's like, it basically gives you an order. But if you have elements that aren't comparable to each other, then the less than or equal to, well, then the order wouldn't be definable. That's why it's called partial order. So another example would be the divides relation. Divides, this using the pipe, x divides y like that. That is a partial order on integers, or at least positive integers. So you could say, for example, that so you could say like 2 divides 3, right? So 2 is comparable to 3. And like 2 divides, sorry, what did I say? 2 divides 3. Why did I say that? 2 divides 4. And 2 divides 6. So 2 is comparable to 4 and 2 is comparable to 6. But 4 doesn't divide 6, and 6 doesn't divide 4. Okay, so 2 divides 4 and 2 divides 6, but 4 and 6 don't divide each other. Also, I said 2 and 3 earlier by mistake, but 2 and 3 is it's another great example. 2 and 3 neither of them divide each other, so they're not comparable. So this is a partial order. It is anti-symmetric, it is transitive, it is reflexive, but it only allows you to compare some things and not other things, right? So if you're using this divides notion as the way of saying what comes before what, you can say, you can say that 2 comes before 4, and you can say that 2 comes before 6, but as far as which of the 4 or the 6 comes first, there's no way to determine that because neither of them divides the other. So if you're using this as your method of ordering, it doesn't completely order things. So it's kind of cool. You can kind of do stuff like you can build these kind of intricate diagrams. Looks sort of like this. And 4 is related to 8. And 4 is related to 12, and 6 is related to 12. But you have you have sort of like some amount of connections and things, right? But not all the connections. 14 would be up here on its own without none of these things would have arrows going to 14 because none of them divide 14. So you have this sort of like intricate connection where you can say 2 is less than via this partial order, all these other things, right? But these other things are not necessarily comparable to each other. Okay, so so the less than or equal to is our like touchstone sort of. We can go back to that as our sort of typical example of what a partial order is, because it's the most familiar one, but it has the problem that it is not just a partial order. It's also what's called a total order. A total order is one in which any two elements in the set are comparable to each other. So a total order takes the entire set and it establishes an ordering for the entire set. So any two things can be placed in order, right? Using that relation. So one of the things I should mention here is that we think of this less than ordering as the natural ordering of numbers, but that is not necessarily, that's not necessarily true. I mean, it is very natural. Don't get me wrong. Like, it totally seems natural to say that like 2 is less than 5, right? But it doesn't have to be. That doesn't have to be the only way that you define an ordering on the numbers, right? So what I'm saying is there's other relations that have similar properties: reflexive, antisymmetric, and transitive, very similar to the less than or equal to, which would allow you to establish different meanings of order on a set of numbers, integers, for example, that is not the same as the one that we're used to. This can also be used to like define order on things that seemingly like elude the notion of ordering. So like subsets in a power, like elements of a power set. So take, for example, oops. Say you have a set A, and it contains like 1, 2, 3, and 4. The power set of A, has everything like the empty set and all the singletons and all of the like pairs and then all the triples and so on. It's got all these different things in it, right? And you can define the like subset or equal to relation is a partial order on that power set, on the set of all the subsets of A. So then you'll be able to say, like, basically the empty set, because it's a subset of everything else, it is less than all the other things, but a lot of them are not comparable to each other. So the set containing like all these singletons, 2, 3, 4. The singletons themselves, I'm actually just going to do 1 through 3 because we're running low, we're running short on time, and I want to show you the full diagram. So I'll make it a little smaller. So those singletons are not comparable to each other. So you can't draw arrows in the digraph for this relation. But then if you look at the different possible combinations of elements together, like this, you can say, well, 1 is a subset of 1, 2. So in our ordering, 1 is less than, in a sense, the set 1, 2. And 1 is less than 1, 3, but it's not comparable to 2, 3. 2 is comparable to this one and this one. 3 is comparable to this one and this one. And then you have the full set, 1, 2, 3, of which everything, they're all subsets of that. And this whole structure, this forms a cube. Like you can kind of see, let me see if I can draw the cube here. You can kind of see the faces of the cube. There's a square face. There's a square in the background here. And then there's squares on the like the side faces. Like here's one on top. And so on. So this structure of relationships between elements in the set forms a cube, and you end up producing that, you end up like discovering this kind of connection between a set with a partial order defined on it and the geometry and like a geometric figure. And so this leads you into all these cool connections between geometry and set theory, which are sort of, and the thing that ties them together is this idea of how do you define what it means to put things in order, and depending on how you define that, you can end up with different geometry properties on a set, and that is super cool. So this area of mathematics, I just wanted to like introduce it to you because it's super cool and neat, and also it has there's a lot of things to explore on the topic of ordering and how do you put things in order? How do you put the real numbers in order, for example? Is it like a tough question related to this? Yeah, so I mean, it's not that tough actually, because you can use this less than or equal to. It's a total order, but there's also something you can read about in the textbook called a well order, something that's a set being well ordered, and that has like an extra requirement on top of it beyond just being a total order, has some extra requirement, and that doing that with the real numbers is pretty hard. But anyway, that's it for today, folks. I hope you had fun. I'm gonna stop recording and see you next week.